ready to learn about the Northern Lights? Did you answer? Are you ready to learn about the Northern Lights? Isaac, it was your birthday yesterday, wasn't it? Isaac is 8 now, and Jessica, I believe it's your birthday today. So you wanted to learn about the Northern Lights. We are going to really learn about them. Before that, I want to show you the worst puppet show in the world, okay? Because I just need to tell you a quick story. I want you to imagine that you're walking through the park and you see an alien spaceship in front of you, and an alien beams down, and the alien walks down the steps and immediately sees a dog, and the alien runs over towards you and says, "What is that? What is that? It's amazing. I must know all about it." And you say, "Well, it's a dog." And the alien says, "What is a dog?" And say, "Well, it's an animal." And the alien says, "What is an animal?" And you say, "Well, it's like something that breathes." "What is breathing?" It's something it's like it shows that you're alive. What is alive? You see my point. Would you think, answer yes or no, would you think that the alien was stupid? No, of course you wouldn't. You wouldn't think it was stupid. Would you think, I am never going to be able to teach this alien what a dog is? No, you would just be thinking, okay, this alien has got a lot of stuff that it hasn't learned yet to get to the bit where it learns about dogs. You're going to need to go back to the beginning. That's what we are doing with the Northern Lights today. I'm going to tell you all about them. We're going to go back to the beginning, and then in the end, we're going to do some really top level stuff, okay? Some sort of definitely A-level stuff that you should learn when you're 16, 17, 18, but I know you can handle it. All right, if you've seen the air lesson, then you've seen these pictures already. If you haven't seen the air lesson, then get your brains working a bit. Which one of these do you think looks most like what air is? Okay, so in our air lesson, I showed you this at the beginning, and then I showed you at the end, and hopefully you'd learned some stuff and you'd realised which one is most like air. It doesn't matter if you don't know, I'm going to tell you. What we decided is that air is made of particles all around us. That's what we're breathing in, particles of lots of different stuff. So well done if you spotted this one, but this one's the most like air. It's lots of different types of particles in the air. And then in our electricity lesson a while ago, we had to dig a little bit more into what particles are, and we learned that that is a very simplistic model of a particle, to just say that it's a ball. We talk about particles a lot, don't we? Everything in the world is made of particles. But what actually are particles? If you could zoom in, then you might get an image that looks like this. Okay, it's a model. You wouldn't actually see this, but this is more accurate. You would see that a particle of air is actually made up of different particles. A positive particle in the middle, surrounded by negative particles spinning around it, and these little negative particles are called electrons. That's all you really need to know for this lesson, is that electrons whiz around in a particle, and the proper word for this particle is an atom. This is a lot, but don't worry, I'm going to use these words again and again. That's all you've learned so far if you've watched all my lessons. Today we get to zoom in a little bit more and see that these particles that everything is made of are made of a positive particle in the middle, negative particles called electrons whizzing around the outside, and the electrons are in different, what we call shells, like different circles. The electrons aren't just any old place, they're stuck in these little shells. So these ones are going round and round and round like that, and these ones are going round and round and round and round like that. And we're going to get to this right at the end. It's very important to know this to understand how the Northern Lights works. People asking for shout outs. If you've got time to stick around the end, it's not a really long lesson, this one. I think we can get it into half an hour. I'll do lots of chatting and shout outs at the end. I'm just going to stay until I've said all your names, if you want me to say your name. Okay, so that's atoms, and it's actually really, really easy, surprisingly easy, to pluck electrons off atoms. That is indeed what we did in our electricity lesson. It's what we're going to try and do today. Guys, I have to be honest with you, I don't think that this making lightning experiment is going to work. I'm going to try and do it anyway. I'll tell you why. It's because where I am, it's very humid. That means there's a lot of water particles in the air, and this experiment does not like water particles. But look, I put my fluffiest pyjamas on specially anyway to get some static electricity going, so we'll give it a go. Maybe there's not as many water particles in the air. where you are. I said that all you need... This is so awkward, I don't know why I'm doing this. Down here. I said that what you needed for this experiment... Yeah, this is ludicrous, I can't do that. I'm very hot because I've had the dehumidifier on in this room, trying to get water out of the air. You need 2 plastic bags, and you need some kind of metal cake tin. You've got to take this plastic bag and rub it against something very woolly, okay? So I'm going to use my excellent pyjamas. Yeah. Just 1 plastic bag, make it flat so that you can put a cake tin on it without it touching anything else. The cake tin's just going to sit on this plastic bag. Sarah, this is your first time joining. What a strange view for your first time. I'm so sorry. We're rubbing a plastic bag against something woolly. And what that is doing, incredibly, is it's... I can't remember which way around it is, but I think it's pulling electrons from your woolly trousers or whatever it is and putting them on the plastic bag. That's what static electricity is. Watch my electricity lesson if you want to learn more about static electricity. So, I've got this bag really rubbed. I'm just going to put it on the floor. There we go. So technically, in an ideal world, that's got lots of electrons on it now. The other bag you're just using as a handle. So don't touch the cake tin with your hands now. You can only touch it with the plastic bag. And what you do is, little story time spoiler there. You pick up the cake tin with the plastic bag, you put it on top of the other plastic bag, making sure that it doesn't touch any carpet or anything like that. And then when I did this in my living room a week ago, all I did then was touch the cake tin and I got the most gorgeous spark. And it hasn't worked at all. I am here in this incredibly sweaty room for no reason. Oh, it's your second live vid. Well, I hope you stick around for the third, because that was pretty disappointing, wasn't it? Did that work for anybody? I'm watching the comments. Did anybody get a spark? What I'll do is I'll wait until it's not a really humid, sweaty day, and I'll go live when I know that it's working, and then you can watch the live video again and do it with me then. But anyway, what we're supposed to see is you put your finger on the cake tin and you get a spark of lightning. And it's like proper lightning, because all it is a string of electrons flowing from the tin, because you've put electrons onto the plastic bag. And electrons don't like being near each other. So the electrons that are in the cake tin jump off the cake tin and into your finger. It's brilliant when it works. We'll get it working, don't worry about that. But what I wanted to show you is that electrons move really easily. They do it in the sun all the time. Here's my picture of a sun. It's a good sun. It looks a bit like the Storybot sun. If you've ever seen the Storybot song about the planets, look it up, it's excellent. The Storybot song, I think, has this orange bit around the sun. That bit's called the corona, and that sends off something called coronal mass ejections. It's called solar wind, and all solar wind is... I've got pens today. Look at this, any colour you want. I'm a proper teacher now. This solar wind, all it is particles in the sun escaping, or electrons indeed, escaping from the sun, flying off out into space at 1 million miles per hour. Just this wind of electrons comes off here. They're travelling so fast that the sun's gravity can't hold them back, and they fly towards us. They actually travel for up to, it's like 11 billion miles. Just charged particles, electrons and a few other bits. They fly towards the Earth, okay? We're going to get to why that has anything to do with the Northern Lights. But first we have to look at magnets. We're going to do magnets and then story time, and then put it all together. So hopefully you have got a couple of magnets and they are working. These are my magnets. Don't judge me. You can do this with any colour. Angela, it works! No! Angela got a spark. Did you get a spark? Ah, oh, you lucky devil. Must be in quite a cold part of the country. So we're just going to have a play with these magnets, okay? All I want you to do is see if you can get your magnets to stick together. You probably can. So magnets are attracted to each other, but you can possibly also get it so that you can feel that they're pushing away. Can you do that? Yeah? Can you change your magnets around so that you can just feel a very, very gentle push. Now, how we draw that, how we draw a magnet. I'm loving having this whiteboard thing. I have actually ordered a whiteboard now. My first stream of support came in from my wonderful patrons. I'm buying a whiteboard, thank you so much. But basically, a magnet, all magnets look like that. They've got a, okay, fine. They look like that. There you go. All magnets look like that. They've got a north end and a south end, and the north sides push away from each other and the south sides push away from each other. But if you put a north and a south together, then they're attracted to each other. Did you notice that you don't have to touch the magnets though to feel a force? Like you could hold them, these are really pathetic little magnets, so I have to hold them really close, but still you can see that there's a gap between them when I start to feel a pull or a push. What is that about? I mean, I know it's magnets, isn't it? Yeah, boring, we all use magnets all the time, but what actually, like, how is that happening? There's nothing there. How can one magnet know that another magnet is there? Even though it's nothing to do with air, the air isn't carrying anything to and fro. It's not like sound where air carries sound into your ear. You could still do this on the moon and it would work. And it's because these magnets are giving off what we call a magnetic field. So magnets and other bits of metal can feel other magnets because magnets give off electric fields, magnetic fields. I'll show you. So some of you know this. If you've seen my animals lesson, we talked a bit about magnetism. The Earth is a magnet. It's not quite a magnet like this. It's not a permanent magnet. Inside of the Earth is made of iron. And that iron is churning around and moving and generating electric currents which generate magnetic currents, and the whole Earth has got these enormous magnetic field lines running around it, you see. And at the North Pole and the South Pole is where they go in. Okay. Notice that the north of the Earth is the South magnetic pole. That's because they actually swap over every few thousand years, but that's something else. We'll try and keep this quite simple. So the Earth is a magnet, did you know that? And the Earth has magnetic field lines. Let's draw them on now because they are very important. Let's sort of go all the way around like this. Magnetic field lines always travel from the north and to the south. I remember it by thinking that it's kind of like people in Britain. Most people move from the north to the south. So don't forget, the south is on the north side. It's all a bit weird. So those are the Earth's magnetic field lines. So the solar wind, these little electrons, are travelling towards the Earth's magnetic field. If these guys get to Earth, they're going to mess up all our electric circuits. They're going to ruin all the computers and stuff that we use on the Earth. What's going to happen? Let's go to story time, and then I'll tell you. Here we go. Story time is when we're really going to dig into some quantum physics today. I'm quite excited about this. A lot of people that I've been wanting you to meet for quite some time. Again, if you've seen my very first lesson, my rainbows lesson, then you might remember this guy, Isaac Newton. You can learn about him in my rainbows lesson, but essentially Isaac Newton showed the world that white light is made of all the different colours of the rainbow. And this is one of the ideas of many that we call classical physics. So at the time, everybody was convinced that light is a wave. Okay? Sounds a bit weird, but light is a wave. It behaves just like a wave. Like people at the time in the 1600s, they knew this because they'd seen water waves travel through tiny little holes, and they'd noticed the funky pattern that comes out the other side. And if you put a light beam through a little hole like that, a really, really, really little hole, you get the same kind of funky pattern. So it's obvious, isn't it? Light is definitely a wave. Easy. And people thought this for hundreds and hundreds and hundreds of years, until in the early 1900s, a chap called Max Planck came along. Max loved physics. If you don't know what physics is, it's the type of science, it's the study of light, sound, like rainbows, music, springs, energy, all that stuff. Max absolutely loved it and studied it at school. He was very famously told by his physics teacher that he shouldn't study physics at university because everything to do with physics had already been discovered. I'll say that again. Max Planck is getting told by his physics teacher, don't bother studying physics at uni because there's nothing new to learn. You won't get famous for studying physics. No, we know it all already. But you know what? Max didn't want to be famous. He didn't want to make amazing discoveries. He just wanted to learn more about his favourite subject. So he did go to university. And after that, he got a job as a professor in Berlin, where he started working on a very, very tricksy problem. It was a problem that classical physics could not explain, okay? The problem was just how do certain objects give off light? We know that they do, but Max and all his scientist friends, they just couldn't work out how certain objects give off light. Like the maths just didn't work. They tried and tried and tried. It didn't work. Eventually, Max thought for a long time, just like us today, had to do a lot of things that didn't work and try again. In what he called an act of desperation, Max realised that if he decided that light wasn't a wave and instead came in little packets of energy, then it all just worked out. Like the maths worked out, we suddenly totally understood and could explain how this object worked. Now, a little spoiler, this was an incredible thing to discover and made Max incredibly famous, and he won the big top prize in physics. At the time, Max, he didn't know what he'd done. He just sort of mentioned it in a lecture and was like, yeah, no, I mean, obviously light is a wave. We all know that, but this works, so, whatever. It took somebody else to say, excuse me, do you realise what you've done? You've done something quite fundamentally brilliant here. Let me tell you about it. And that person was called Einstein. Let's go and see him. Here we go. Einstein was very good at explaining things. He had a fantastic brain, thought about things very carefully. And he said, look, Max, you know what you've done, okay? Imagine that I'm at a party and I'm giving drinks out to children, okay? Children could have as much drink as they wanted. You could have 5 millilitres, 10 millilitres, you could have 10.5 millilitres, you could have 10 1/10 millilitres, you could have 10 and like 1 atom. It's like a continuous spectrum. Now, we used to think that if light came to this party and the juice was energy, that light could have any different amount of energy it wanted. And Einstein said, no, Max, what you've just said is that energy is more like sweets. And that when the light comes up to me on my stall and wants some sweets, it can't have like 1 1/10 sweets, really, can it? It can't have 1 100th of a sweet. It just needs to take a sweet. And basically, what you've said is that light is not a wave, it's a particle. It can only have a certain amount of energy, like a little packet of energy. So light is a particle. Light is a particle. That's what you've come up with, and that is huge. And then a chap called Niels Bohr said, guys, light can be a wave and a particle. Don't worry about it. We'll study both at once. That's fine. And then a person called Schrödinger said, hey guys, I've just done some maths that realised that electrons aren't particles, they're actually waves, and the whole thing went crazy. And it turned out that Max Planck had given birth to a type of science that we call quantum physics. Classical physics was very, very, very good at explaining the things that we could see on Earth, but quantum physics is absolutely fantastic at explaining teeny tiny little things that we can't see. We wouldn't have computers or the internet without it. My favourite fact about all that is that there was a conference called the Solvay Conference in 1927, and all those people went. They basically got a photo taken together. I was going to say selfie. It's not. It's just a photo, but it's a beautiful photo. You need to go and see it. Max Planck is sitting next to Marie Curie. Yeah, it's just an incredible picture. You should totally go and look at all the different scientists. That's the Solvay Conference 1927. Look it up. All right, so now you know about quantum physics. I think we're ready to finish our story about why the Northern Lights happen. These electrons, the same things that make your hair go static, are flying towards the Earth at 1,000,000 miles per hour. They get to our magnetic field, and Basically, the Earth has got an invisible force field around it. Genuinely legitimate invisible force field. Just like, you know, sort of what happens when Captain America's shield goes up. These electrons get stopped by Earth's invisible force field. And this is the bit that we call the bow shock. So the bow shock is kind of like bending and straining under the pressure of this solar wind flying towards the Earth. And eventually, the magnetosphere, that's the Earth's magnetic field, is under so much tension that it kind of snaps like an elastic band, and the bits of the elastic band fly back around the Earth and sort of twang particles towards the Earth with loads and loads and loads of energy. And these really energetic particles, they travel along with the Earth's magnetic field lines, so they get sucked or pushed, I should say, down to the North Pole and the South Pole. And that's why you only see the Northern Lights and the Southern Lights at the North and South Poles. It's because this solar wind has travelled along with the Earth's magnetic field to get here. So why does that cause the Northern Lights? Whew. I did see a video explaining the Northern Lights for kids, which then said that the electrons high-five particles in the air. That is not what's happening. Remember that air is made of different particles. So up here in our atmosphere, there are oxygen particles and nitrogen particles. Now this solar wind travels down, down, down. It hits these oxygen and nitrogen particles, and it gives them loads and loads of energy. And what actually happens when an atom gets loads of energy is that its electron jumps into a higher shell, just like that. So the atom's like this, just hanging out, all happy, happy, happy. It gets bashed by a bit of solar wind, and one of the electrons goes, and then when the electron falls down again and the atom calms down, whoop, a little bit of light comes out, a particle of light comes out, because energy's got to go somewhere. So it goes into the atom, we call it the atom getting excited. And then when the atom stops being excited, where does that energy go? It goes into a tiny little particle of light, a packet of light, that flips out into the sky. And we see it as the Northern Lights. That was quite fast. But how incredible is that? That solar wind that's travelled millions of miles gets to the Earth and then excites an atom, and then a particle of light is made and comes off. It is very cool, this is very cool. Why do we get different colours? Well, it depends how far the electron jumps and how much energy is given off. So oxygen tends to give off packets of green light, and nitrogen tends to give off packets of blue light. But really rare, you might have seen photos, really rare Northern Lights can be red, and that is oxygen particles really high up in the atmosphere. So the higher up the particles are, sometimes the different colours they give off. The explanation that I saw was that oxygen takes a really long time. It takes like 2 minutes to give off red light, and usually if it's down here, it's getting too bashed and it keeps getting interrupted. But if it's up here and there aren't as many particles, sometimes it gets the time that it needs to give off a particle of red light. And that's the Northern Lights for you. Before I just start doing shout-outs and we start chatting, I want to show you, if you've got any glow-in-the-dark stuff, it's quite common now, glow-in-the-dark stars, my kid's got some slippers, then that is what's happening in your glow-in-the-dark stuff. You're shining a light on like this phosphorus stuff inside your glow-in-the-dark stuff, and atoms inside your slipper or your star or whatever are getting excited and then dropping down and sending off a green light. In case you haven't got any, I'm gonna show you now. I've made like this little tent. And what I have here, I thought we could do a little and very poor experiment. I have a normal torch and I have a light which claims to give off ultraviolet radiation. Now, if light is ultraviolet radiation, has a lot more energy than normal light. Here's my stars. Let's just shine these onto each one and see which one glows better. Why is this not a very good experiment? Because this might be a really, really strong light, mightn't it? And my ultraviolet pen might have been played with so much by my children that it's nearly dead, but we'll do it anyway. So if one star shines brighter than the other, maybe that will be a way of us finding out that some light has more energy than others. Also, glow-in-the-dark stuff is cool, isn't it? We've talked about atoms getting excited. That seems pretty abstract. Let's actually see atoms getting excited. So what I'm doing is I'm just shining my ultraviolet pen onto this material, and the atoms that make up this thing are getting excited, and their electrons are jumping into their higher shells, and every time one jumps down, it gives off a photon of green light. All right, here we are. What a terrible experiment, and I did the ultraviolet one last. Yeah, I mean, that's horribly unfair, isn't it? But it does look like the ultraviolet one's brighter. Anyway, thanks for coming into my little glow-in-the-dark tent with me. That was fun. What else do I need to tell you? Oh yeah, so Northern Lights, it seems like, just studying pretty lights, you know, what for? Actually, if you've seen my tsunamis lesson, you'll know how serious this is. Some scientists think that it's possible that like a tsunami of solar wind could easily come off the sun and get to Earth's atmosphere, and that would totally mess up all our electronic equipment. It would make life on Earth incredibly difficult. So actually, all this work that we're doing on studying the Northern Lights and where the energy comes from and stuff is really, really useful so that we can protect our electronic equipment. So there you go. Thus ends my Northern Lights lesson. So a couple of things to say now. If you haven't followed me on Facebook, please do. I can start giving you adverts if like 200 people more follow me. So sorry, but not sorry. That would be so cool. The other much more exciting thing is I wrote to the lovely, lovely people at a shop called Word United and said, hey, can I have a prize for my people who watch my lesson? And they said, yeah. So if you're supporting me on Patreon, the competition this week is this awesome magnetic lap by Gulp Toys. Still quite a high chance of winning. So if you were thinking about supporting me on Patreon, then the link is in the shop on my Facebook page. If you sign up, you get a little cookbook that I've written, and you get a magazine coming very soon, and there's also a couple of competitions on there now. If you could subscribe to me on YouTube, that would be super awesome. Thank you so much to the people who just keep sharing what I'm doing and telling their friends about it. That is incredibly useful. And now I'm just going to say one big thank you so much for watching. Bye! I've never seen the Northern Lights in real life. Have you? Has anyone seen them? I didn't even tell you what they were, did I? You might not even know what the Northern Lights are. What a foolish person I am. No, I've never seen them. Hiya, Amelia and Jenna. Hello, Harry. Hello, Dylan. Bye, and thank you, Ruth. Holly and Finn. You should have rubbed the light on the stars at the same time. Yeah, I know, I should. I know. I had like a blanket on my head and it was hard, but you're absolutely right. Thank you. Hazel, why does ice float in water? Oh, do any other planets experience the Northern Lights? What a brilliant question. Winnie, Dylan, hello, let's have a shout out. Hi, Dylan. Yeah, they do. Yeah, loads. We are studying them right now. Laura, Burton, you can have a shout out. I really want to answer the ice question. Oh, why can't you always see the Northern Lights? Thank you, Tracy. The Northern Lights are there all the time, but we can't see them in the daytime because the sun is too bright. Usually when stuff freezes, their particles get closer together. When something becomes a solid, its particles get closer together and become much more like regimented. So in a liquid, particles are just floating around however they want, and then in a solid, all the particles slow down and get closer together. Water, when it slows down and freezes, it forms special bonds which keep all the particles very spread out. And we would say, if you watched my hot air balloon lesson, you know what I'm talking about, that it's not very dense. So in a big space, you don't have that many particles. So that's why it floats, because it's less dense than liquid water. Hi Cicely, good to see you. Can we do a lesson on crystals? Oh, I'm really excited about writing a magazine for the people who support me on Patreon, and I want to finish that before I do any sort of big research on another lesson. Why are Northern Lights different shapes? Hey, that's a brilliant question. I think, it's good Good point. I was going to say like the magnetic field line. I mean, they just follow the Earth's magnetic field, so I guess... Yeah, I'll have to look that up. Yeah, no, Liz, it's bad. It really starts the show, doesn't it? If any chemistry questions come on, I'll just get like this blind look of panic. In fact, every time I say, oh, my comments are working, someone's just asked a chemistry question, that's all. And I'm going to go and have a cup of tea and open a window because it is very hot in here for no reason. Still didn't get a spark. Bye.